Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is member surface and solid stress strain analysis in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Chua will also be joining me as today's moderator, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, we will begin with our first example, which will be a stress strain analysis with member elements or 1D elements within our program RFEM. We'll then move on to the second example, which is a stress strain analysis with surfaces or essentially 2D elements. And I'm going to be showing you a new feature in RFEM 6, including line weld joints. Example 3 will be a stress strain analysis with a solid, and that will be our structure over here on the right-hand side, and that is essentially a 3D element. So we'll be working in our FEA program RFEM today, but we'll also be utilizing the stress strain analysis add-on as well as the nonlinear material behavior add-on for that second example. And finally, we'll touch on a report printout documentation at the end of the presentation today. So begin within our main program RFEM here, and I've already created the first model, and you'll notice I gave it a model name. The type of model is set to 3D, and under the add-ons, this is where we want to activate the stress strain analysis add-on. So these are all the multiple add-ons that we could purchase with our RFEM license. So we'll be starting with this one for today. So once we've activated that, we can see our 1D member elements modeled here in our graphical window. So essentially, if I turn this into wireframe view, these are all going to be one-dimensional elements. And this is some type of facade wall. I have defined the material here for all of these members as 6061 T6, and this comes directly from the ADM standard. So if we take a look at our material database, notice I use my filters on the left to filter to the ADM, and under the 6061 category, I chose this particular material for extrusions. If we take a look at the cross sections that are defined within this model, we have a couple of them here. These are just basic parametric sections where I could input in the dimensions here, and the program will automatically calculate the cross-section values for me. Same concept for this second cross-section. Notice I just have rotated it 90 degrees here. So I have modeled all of these members, and the program has went ahead and broken some of these apart here. So perhaps we'd like to design these columns as one continuous member. And even though those members are broken apart, it's not a problem, as we can create what's called member sets. So if we highlight all of these single elements here, and we'd really like to design them as one continuous member, we can always right click, and under the member option, we have what's called create member set. So the program will automatically group all of those together, and now we see them available in our navigator over on the left. I also want to go back to our base data here by right-clicking on the model name. And under the settings and options, I'm going to go ahead and turn on the member representative and the member set representative. So notice we have a couple additional tabs up here at the top. So what the program can do is to group together members that have similar materials, cross-sections, lengths, as well as several other options here. So once we activate these member representatives, we also see them available over here on the left-hand side. And if I turn this into wireframe view, we'll also see those red and blue symbols here, kind of grouping those similar members together. And this will come into play later on with our stress design. I've also applied a couple of supports here. So you'll notice the nodal supports applied at the center line of these small segments. And then we have a sliding nodal support down here at the bottom. So now moving on to the loads. I have created two basic load cases for our facade wall here, just a basic dead load. Notice self-weight is active, and I've also created a wind load case. So once those load cases are created within this dialog box, we would actually apply the loads to the structure. And again, for the sake of time, I went ahead and did that. So if we turn on our loads for dead load, you can see that this facade wall is likely going to be supporting some type of glass panel. So I wanted to attach the glass panel and represent them as basic point loads along these horizontal members. And if we double click on these loads, you'll see here that we can set the load type to force, but the load distribution is set to concentrated, where I can set the number of point loads along the member length. So I set the magnitude here at negative 0.8 kips. In the global Z direction, we have 2 point loads along the member length set at a distance of 10% of the member length, then an additional 80% of the member length. And not only that, but with these glass panels that we're trying to represent, perhaps they're not necessarily applied right at the center of these members. So we have the ability here to turn on the eccentricity of these point loads. And now we get an additional tab here where we can apply an eccentricity. I've set this to 6 inches in the local Z direction of the member based off the center of gravity. So now we have an additional torsional moment applied to these members based on these glass panels being attached there. You can also modify this to the shear center as well. So I've applied these point loads not only to the bottom horizontal members, but you can see them applied up here, the upper members as well. Moving on to the wind load, we can see that wind load generated here as a lateral load, and I took advantage of our load wizard over here in the project navigator and what's called the member loads from area load. So if we take a look at this applied load, you can see here that I've set the load direction in the global X direction here based on the global axes. The load magnitude is set at 0.02 kips per square foot. And then under the second tab, this is where we have two options. Either we could use the ability to select the corner points of the area load, or we can select the cells graphically. So the program can actually detect here these closed cells between members. We can graphically select them with our options here, our selection options. And when we do this, all of those cells are automatically populated within this table. So what we'll see here is that applied lateral area load based on a closed area for these members shown here graphically. And we can always right click on this load to display separately. So essentially this is going to be the member loads that are applied based on the tributary area of each one of these members. But we can always right click here to uncheck this display separately for a little bit of a cleaner look there. So now that the loads have been applied to the structure, let us go back into our load cases and combinations, and we're gonna back up a step under this base data. So currently I'm generating the load combinations automatically according to the ASCE 7, but you can see here we can select the NBC, Eurocode, and many other international standards. So when this option is checked, those load combinations will be automatically generated according to the standard. The design situations are really important. We have two design situations automatically created, LRFD for our factored load combinations and ASD for our unfactored load combinations. But notice we activate these design situations for the add-ons. So the add-on that we turn on, remember, was the stress strain analysis. So we'll be using this design situation once we get into that add-on for the design portion. Now, if I'm not so interested in my unfactored load combinations, let's say serviceability is not really a concern, we can delete this design situation or we can simply deactivate it up here in the upper right-hand corner. And under the last tab, the load combinations, this is where we see the load combinations individually listed out based on the ASCE 7 and only according to the load cases we have defined, that dead load and that wind load. So now that the load combinations as well as the design situations are set, what we would like to move on to is the stress strain design configuration. So we're technically ready to run the analysis, but the huge advantage of RFEM 6 is the integration of these design add-ons so that we can run one continuous workflow. So what I'd like to do is to right click on my folder here to collapse all these folders. So maybe it's not so overwhelming. And because we have activated that stress strain analysis add-on, we now see an additional folder over here on the left. And included in this list is what's called the member configurations. So we'll double click on this to take a look at the default options. Now, notice that these are all of the available stresses that we can calculate for these members, and that includes normal stresses based on axial loads, based on bending loads, and the list is rather long, but we've taken the liberty here to suggest a few of these stresses that you might be most interested in. For our example today, let us assume that we really are only interested in designing the von Mises stresses. So when I take a look at this, I make sure my checkbox is on, and notice for all these stresses, the equations along with the variables are listed over here on the right. And in the second column here is where we set the limit stress type. Now, currently it's set to the limit equivalent stress. What this means is the program is going to refer to that ADM material to determine what the limiting stress value is. Now, alternatively, we can set this to user defined, and I can simply type in the user defined limit in this third column. But let us go ahead and leave this for now set at the limit equivalent stress. The other nice thing about these configurations is that we can give this one a name. We'll call it von Mises. We don't necessarily have to apply the same configuration to every single member in the model. So if I'm interested in applying the von Mises here only to my vertical members, I can graphically select them here. And once I click OK, we'll see those members populated in the upper right-hand corner. Now I can make a copy of this configuration, and instead of von Mises, let us turn on the equivalent stresses based on the Tresca hypothesis theory. And we see the relevant equation here that will be used. We can give this one a name that will be called Tresca. And we're going to assign to all of our horizontal members. So we can select these members one by one here using our selection box. And once we're done with this, we click OK and we see the members populated in the upper right-hand corner. So we are now ready to run our calculation. We can go to calculate, calculate all. The program will generate the mesh. It will move through the load cases and combinations for the static analysis, and then it will move through the stress design. So once this calculation is done running, you'll notice that we can view any one of these load combinations, for example, from our drop-down menu. And over on the left, we have both the static analysis and the stress strain analysis. So if we start off with the static analysis, we can view information like our global deformations, our support reactions, but of course, we're interested in here all of the available stresses as well. So we can view these stresses on the member, including normal stresses, shear stresses, of course, the von Mises stresses. So again, this is the static portion of the analysis. But we're also interested in the stress design based on those configurations that we've just set. So what we can do here is to jump to the stress strain analysis within this dropdown. And if we take a look at our table results, you'll notice that we actually get an error for each one of these stress ratios. It just simply says non-designable. So we'd like to take a look at this in a little bit more detail. And I'm going to go into my result details here. And this is going to give me a little bit more information. It tells me no limiting stress defined. Please correct in the member configurations. Well, if we refer back to our aluminum material, and I'll visit this here under the basic objects, the materials, we take a look. You'll notice that the material values have many different values set here under the strengths, depending on if the member is in tension, in compression, and shear, and so on. So aluminum materials are a little bit different than, say, what we would see with steel. A36, for example, has a very clear yield strength of 36 KSI, but aluminum ADM materials do not. So the program simply doesn't know which one of these to refer to. So we can easily fix that here by going back to our member configurations. And under our von Mises configuration, instead of using the limit equivalent stress, perhaps we set this to user defined instead, and we pick one of those strength values for that ADM material, such as 35 KSI. And under the Tresca, we need to do the same thing. So we'll set this to user defined, and we'll also set this to 35 KSI. And we click OK. So if we revisit here our stress strain analysis, we see here our input data, and we see the design situation. Remember that LRFD design situation, and we're designing all of our members. So our static analysis remains the same here, but we do need to rerun the design portion according to this add-on. So we'll go ahead and initiate that, and now we should see some results here available in our table format. And we can take a look within this dropdown, the stresses on members. So we look at the tab here, stresses on members, and sure enough, we have our column here of existing stresses for each of these members, but we also have the limiting stress of that 35 KSI, and ultimately we're getting a stress design ratio. Now we also can view these stresses by member set. So remember those continuous members that we created for these vertical columns. We're also going to see our stress design ratios for each one of these continuous members. If you also remember, we activated the member representative, and we're only getting one value here. And we can think of this more so as an envelope solution. So we're grouping together all of those horizontal members, and we're going to give you one value here for the existing stress, the limiting stress, and the stress design ratio. Same concept for the member set representatives. The other thing that we can view for any one of these results here in our table format is to take a look back at these result details. If you remember, this is where we got more information about our error message, but now that it solves, what we actually see is the stress ratio. We see that same equation given to us on how we're going to calculate, for example, the von Mises stresses. We see all of our variables given. And what else is nice within these details is we can turn on the stress diagram within this section. So currently we're looking at that cross section at the location of x equals 0.5 feet along the member length. And we're currently viewing those von Mises stresses graphically here, but we can use the drop down to choose the third option, stresses, here as well. And the stresses is going to allow me to view all of the normal stresses. Perhaps I want to take a look at the shear stresses. So we can add this information to our printout report and just get a little bit more information about what's going on for this particular section at this X location. Now, of course, in addition to the table format, we have all of our information shown graphically here under the stress strain analysis. For example, we can view the stress design ratios that are currently turned on according to Tresca, or perhaps we want to turn on the stress ratios according to the von Mises. Okay, so that will wrap up this first example with one-dimensional members. For our second example, I'm actually going to create a new file because we will model this one from scratch. Pretty basic structure, so we'll give this the model name of base plate, whatever that may be. And the type of model will be set to 3D. And under the add-ons, again, we want to activate the stress strain analysis. And we're also going to activate for this second example, the nonlinear material behavior. So we'll get into this a little bit later on, and we can click OK. So now we're presented with a brand new model here within RFEM. And the first thing I'd like to do is to right click on my grid settings down here at the bottom. Well, currently everything is based on a spacing of 1 foot. So I'm going to go into my units here, and instead of using the lengths unit of feet, I'm going to change this to inches because we're going to be working with a much smaller scale here. I click OK, and instead of my grid point spacing at every 12 inches, we'll go ahead and set this to every 1 inch, and we click OK. So we zoom in here, and now we see our much smaller drawing grid. So we'll begin by drawing a new surface, and we do so within our toolbar up here, and we'll choose rectangle via center. And we need to generate a new thickness and material for this surface. So we create a new definition type here. The thickness is going to be set at 0.5 inches, and we need to create a new material from our material database. We can use our filters over on the left to choose steel, to choose the AISC 360, for example, and we can choose A36 for plates. So now that this thickness and material have been defined, I can click OK through these dialog boxes. I will snap at the origin here, and I'll make my second click at a point of 10 inches in both the X and the Y directions, and we have our first 2D surface element generated here. Now I'd like to add in some openings. This will essentially be our base plate, and we add in the openings to represent where those bolts will connect the base plate to the underside of the surface. Well, we can do so in a similar manner by creating a new opening, and we'll choose the circle option. And then I can just simply click directly on my drawing grid, and I can set my radius by typing it in on my keyboard, such as 0.75 inches. I hit enter, and now we see that opening generated here on the surface. I'm going to represent my bolt elements with a new nodal support. So I create a node to begin with by directly clicking here right at the center of that opening. I right click to exit, and we're going to create a new nodal support. I'm going to generate a new nodal support definition here as well. And what I'd like to do is to restrain translation in the global X, Y, and Z directions, but I'm going to release rotation about those global X, Y, Z. So this pin nodal support is going to represent that bolt taking over those tension forces. So I click OK once again. I'll snap here to that newly generated node. I right click, and we can even right click on the display of this nodal support to decrease the size to something much smaller, so it kind of fits in with the size of our base plate here. I'll convert this to wireframe view, and I'm going to highlight all of these elements that I just generated. And what I want to do here is to make a copy of the opening and the nodal support. So we'll go to our rotate copy tool. We will create a copy, 3 of them. We'll rotate 90 degrees about the origin. We click OK, and now we can see the rest of those openings and nodal supports generated here. Now, the problem is that none of these nodal supports are currently connected to the base plate. That's just because they're sitting in the middle of these openings, but it's not a problem because what we can do here is to choose the option to create a new surface by selecting the boundary lines. And instead of the stiffness type being set to standard, we can choose this option here, rigid. So we'll fill in those openings with a rigid surface. Notice I don't set a thickness, I don't set a material. That's just simply because the stiffness is really, really high for this particular stiffness type. So when I click OK, I can just simply click around these openings here to essentially connect that nodal support back to the base plate. So now we'd like to move on to modeling the column element. And there are many different ways to do this, but I'd like to show you a quick trick that we have in the program. So I'm going to modify my drawing grid in the vertical direction here. We can see that clearly in our graphical window. And I'm going to create a new single member. And this single member is exactly like what we just saw in the previous example. It's a one-dimensional element. So under the section is where we create a new cross section. And instead of one of these parametric sections, I'll take advantage of a standardized section. And the standardized section allows me to once again use my filters similar to our materials over on the left-hand side. And I can filter, for example, to the AISC 15, and we can choose a W shape here, and we scroll all the way to the bottom because all the shapes are listed, but we choose a W 8 by 35. Now we also need to generate a new material. So we access our material database once again using our filters over on the left, but this time we choose A992. Click OK, and now that new material is associated with this W8 by 35. I click OK. Through these dialog boxes, I snap at that origin, and my second point is going to be up here at 40 inches in the vertical direction. And we have our column generated. But the problem is when I turn this to wireframe view, again, this member is just a one-dimensional element modeled here at the centroid. So we want to convert this to 2D surfaces so we can do an in-depth stress analysis and design. What we have here in the program is the ability to right-click on this member, and under the members menu, I can actually generate the surfaces from that W8 by 35. And notice everything was converted to those 2D surfaces. Now the flanges, the web, everything from that W8 by 35 was converted into these surface elements, including the thickness as well as the material. So we don't need to make any modifications, assuming we still want that same cross section. Okay, so now that we have modeled this column, we do need to apply a surface support down here at the bottom. And what's going to happen with downward deflection, of course, this base plate is going to bear on some other type of surface that we didn't model today. But in uplift, we want that surface support to fail. And instead, we would expect our bolts, or what we have represented here with our nodal supports, to take over those tension forces. So we create a new surface support within our tools, and I'm going to create a new definition type. We'll go ahead and restrain the shear based on the local X, Z, and YZ axes of this surface. And for my vertical translation, again, based on the local Z axis here, I'm going to set a spring constant of 1e to the 6. So it's really recommended in almost all cases with a surface support not to fully fix it in the vertical direction. We just have better convergence here with the calculation when we set a spring constant instead. And of course, we want to take advantage of this nonlinearity. So RFEM is a nonlinear analysis program. All of the geometric nonlinearities are automatically included within this base program. So this is where we can set failure if positive contact stress in the vertical direction. So now with uplift, we should see that support completely fail, but in a downward deflection, that support will be engaged again. We click OK, we can snap on that base plate and we see that surface support applied here. And similar to the nodal supports, we can right click and use our slider to decrease the size of this. And we can also increase the number of elements we're seeing here or decrease them depending on what we see fit for our model. All right, so essentially the modeling portion is complete. Let us touch on the FE mesh. If I go to calculate, generate mesh, what you'll see here is that the mesh is entirely too big. We're really getting very few mesh points here, which in turn is not going to be an accurate analysis. So it's very clear that we need to refine this FE mesh. Once again, going to calculate, we have mesh settings. So instead of the default 1 foot or 12 inches for the target length, we can set this to something much smaller, such as 1 inch. I click OK and apply. The program will generate that FE mesh, and we can say that this looks much better. But if I zoom in here on these openings, I really only have 4 mesh points around the circumference. So perhaps we want to refine the mesh a bit more around these openings. So I can hold down my control key here to select all 4 of these nodes. I'll go ahead and double click, and we have the ability to activate the mesh refinement under these particular node numbers. Now we get a new tab here where I can create a new nodal mesh refinement. And we can set the radius of this nodal mesh refinement to 3 inches. The inner target length will be 0.1 inches, but we'll transition back to those global settings of 1 inch. I click OK. I click OK once again, and now we see that FE mesh refinement symbol shown graphically here within the model. Perhaps we'd like to do the same thing at the base of the column and refine the mesh a little bit further around these lines. Well, I hold down my control key to select all of them. I can double click to edit the line, and in a similar manner to our nodes, we can activate the mesh refinement for these particular lines. Under the mesh refinement, we create a new definition, and we're going to set the target length to something like 0.2 inches. I click OK. Then we can finally go to calculate, generate FE mesh, and we'll see here a much more refined FE mesh at the base of the column as well as around those openings. So everything seems to be good to go now. Moving on to loading. Essentially what I would like to do is to visit my load cases and combinations here. And we have a default load case that's always created called self-weight. We'll let us go ahead and rename this one to dead load. We can leave the self-weight active here. I'll create a second load case for our very simple example today that will be live load with the action category of live load. So now that these two load cases are generated, what we'd like to do is to actually apply the loads to the structure. And the loads are going to be applied as a point load at the top of this column. But the problem is if we apply a point load as the model is now, we're going to get a singularity because that load isn't going to be distributed over the entire face for the top of this column. Well, we can fix this by drawing a new surface yet again, and the type will be rectangle. And we're going to set the stiffness type to rigid. So we know we're familiar with this rigid. We set it at the openings where our bolts are located. So we'll use the same stiffness type here. I click OK. I click once on the left of the structure and a second time on the right of the structure. And if we turn this to a rendered view, we can see that rigid surface shown here. So now I can create my first point load, and I'll do so by activating here a new nodal load. I get my dialog box where I can change my load case here to dead load, and I set the force as -20 kips in the global Z direction, and I can graphically choose which node to apply here, node number 14. If I hit apply and next, the program will automatically apply that load within the background, but I'm still within the same dialog box so that I can use my dropdown to choose live load, modify this magnitude here to 5 kips in the global Y direction. I click OK, and now we should be able to select this node, click OK once again, and we see that lateral load applied here. So going back to dead load and live load, both of those loads should be sufficient. Going back into our load cases and combinations, we've created these load cases, but we want to combine them, of course, into a load combination. And we also need to check out our design situations. So back under the base data, if we're thinking, well, we'd rather manually create those load combinations instead, all we need to do is to simply turn off the combination wizard. And notice a few of those tabs disappeared here at the top. So what this gives me the ability to do is to still create these design situations, which were automatically generated based on the ASCE7. But perhaps, again, I'm not interested in my ASD design situation. I can completely delete it. I can even take this design situation here and rename it if I'd like. So we'll just call this one design situation 1. Maybe it's a little bit more code independent, but it's still active for this stress strain analysis. Remember, we have to have a design situation that all of the load combinations are placed under for these add-ons. So looking at our load combinations tab, it's empty because we need to manually create these. So I'll generate a new load combination here. Perhaps we change the static analysis settings to linear first order rather than second order. And under the assignment, we can select both dead load and live load. We could adjust the load factors if we'd like. We'll go ahead and leave this as a simple 1.0 dead plus 1.0 live. We click OK, and now we should see that load combination available to us along with both of those loads being applied here graphically. All right, so let us talk about those stress strain configurations. Remember, because we have activated the stress strain analysis, we have this folder available to us over on the left-hand side. I can right click here to collapse all of those again so it's not as overwhelming. And the first thing I'd like to do is to right click on these settings for the stress strain analysis. Now, by default, in order to design the strain, it's actually turned off. We'll still get the strain analysis results in the static analysis portion, but as far as the design within this add-on, we can activate it here with the strain analysis. So we'll see how that looks a bit different from our previous example. And I click OK. So now instead of member configurations here, we have surface configurations because we have only 2D elements within this model. So I take a look at my configuration details, and this list should be a little bit different than what we saw with our members. So we see all of the available stresses we can calculate, the relevant formulas over here on the right-hand side. And again, we've taken the liberty to check on a few of those that we think you'd be most interested. But for us, what I'd like to do today is to only activate the von Mises max. And we see the equation given here. So just to keep it simple for this particular example. Now, the limit equivalent stress that it's going to refer to, this should not be the same problem that we had with the ADM material. We know with A36 material, with A992, we only have one yield strength. So that should be fine for this example. Notice under these strains, we have all of the available strains that we can go ahead and design as well. Now I'm going to turn most of these off. We'll only activate the von Mises strain. Notice you can set here the plastic strain limit. So this strain limit is only applicable when we're actually doing a plastic nonlinear material design, which we will be in just a minute, but just know that the second column is only available for that nonlinear analysis, not for the linear analysis, which is what we're currently under. So this is going to be assigned to all of the surfaces. I click OK. If we want to take a look at here within our dropdown, the stress strain analysis, input data, remember we have our single design situation here. The objects to analyze, all of my surfaces are turned on. We also can turn on what's called the stress ranges. So we activate this for all of our surfaces. What this just means is that we'll be able to give you the minimum stress, the maximum stress, and the stress range for each one of those surfaces. And we'll see what that looks like in just a minute. So we're now ready to run the calculation. We go to calculate, calculate all. The program generates that mesh. It will now run through the load cases and combinations for the static analysis. And then we move on to the stress strain design. So we're currently looking at our load combination, and we see here our static analysis results. And we currently have the deformation turned on, but we're probably, again, most interested here in topics like our surface stresses. And we can view the surface strains. Now, again, with the static analysis, we have everything available to us. It's just the design portion that we limited it to the equivalent von Mises stresses, for example. But we can take a look at here the static analysis for those von Mises stresses. And I scroll in here, we certainly have some high stress points. You know, these maybe could be attributed more to a singularity. But notice that the stress value here at these high peak points is 163 KSI. And there's something I'd like to discuss a bit further that's really important when we're viewing our results here on these very small scales for these steel type connections, for example. Under Calculate Result Smoothing, these are the various options for how we're going to smooth the results so that we can present them to you with these ISO bands or these colors that are available here in our navigator. And they really can affect the results and how we're actually viewing them depending on which setting we have set. So what I'd like to do is to go back to the PowerPoint to explain this in a bit more detail. So notice here for my example, I have two adjacent surfaces, surface 1 and surface 2, with the dividing line right down here in the center. Well, the first option in that list that I just showed you is the constant on mesh elements. What we're going to do is to average out the value with each FE element and show a constant distribution display. So notice each one of these FE elements has a single color applied to it. However, each element is very independent of the one right next to it. Now, the average values for each element are displayed at the FE mesh point. So this is 4 values total. So notice we have 4 FE elements at a single point kind of surrounding it. So inevitably, we're going to show a total of 4 points here. Now, this is really recommended for these small scale models, such as maybe what we're looking at today, as well as nonlinear plastic design. And we'll see how when we change to this setting, exactly how our results might look. The second option is non-continuous. This is where we have a varying distribution over each element. So notice now for each FE element, we might have multiple colors here, but there's still a non-continuous display between the adjacent elements. So each element is still very independent from the one next to it. We are going to display the corner values of each FE element at every FE mesh point for a total of 4 values. So again, we have 4 total values here based on those 4 FE elements surrounding that single mesh point. The third option is continuous within surfaces. So this is the default option and currently what we are viewing in our example today. Essentially, we are going to use a smoothing algorithm to smooth these results between all of the elements within a single surface. So now notice that surface number 1, all of these values are kind of tied together between all of the elements, yet it's still a non-continuous display between adjacent surfaces. So each surface is now independent. We're not going to tie those values together. The average value of the elements is displayed at every FE mesh point. So we now have one total value here for each surface because we're kind of averaging those out, smoothing them all together. But notice we have 2 values here where the 2 surfaces kind of butt up against each other. Now, the final option is going to be continuous within all surfaces. So we use that smoothing algorithm to smooth all results between all elements in the model. And there's now a continuous display between the adjacent surfaces. So now we're not going to really see that boundary line between surface 1 and surface 2 and can kind of tie all of those ISO bands and colors together. We're also going to have one average value of each element displayed at the FE mesh point. So now one value is given here. So let us go back to our example to see how this really affects our results and if it makes that much of a difference. So again, the default option here is continuous within surface sets or otherwise within surfaces. And our von Mises stress is 163 KSI. Well, I'm now going to modify this to constant on mesh elements. I click OK, and remember that's that first option we covered in the PowerPoint where each FE mesh element has its own average value. And notice my von Mises stresses is now 90 KSI. So it was significantly reduced because we're no longer trying to tie all of those stresses together within a single surface. So this is why it can really impact how we're viewing our results. So now that we have changed this, notice I didn't need to rerun the static analysis. It's just really how our results are presented to us. But what I would like to do is to go to the stress strain analysis here, and we do need to rerun this calculation. The program says, well, wait a minute, it looks like the stresses I need to compare to have changed. So now we can view here the stresses on the surface. And when I take a look at, I have my existing stresses in my first column here, the limiting stresses, which are either 36 KSI for my A36 material or 50 KSI for A992. And ultimately, we're getting a stress ratio. And what we see here are the stress ratios are very high. 2.06, for example, well, we clearly know that these materials are not going to be able to take on these high of stresses. They're simply going to yield before we get to this point. So this might flag us that, okay, it might be ready to move on to a nonlinear material analysis instead. And it's actually quite simple to make that change here within the model. If we go back to our materials here in our project navigator, if we take a look at the materials tree, and in particular A36. So I double click on this material, and what you'll notice is that the default material model is an isotropic linear elastic. So just a simple linear material default in the program. But if you remember, under the base data, I activated the nonlinear material behavior add-on. This add-on now releases all of the nonlinear material models. And for us, we're going to take advantage of this isotropic plastic for surfaces. Now under the second tab, we can see here the yield strength is set at 36 KSI. So essentially none of those FE elements should exceed this 36 KSI. Under A992, we can make that same change by changing it to an isotropic plastic. And notice under our second tab, we have a yield strength here of 50 KSI. So once we have made that change, all that we need to do is to rerun the calculation. So the program needs to go back through the static analysis. It's also going to go back through the stress strain design. You'll notice it takes just a split second longer here because we now have a nonlinear material. But ultimately, reviewing the static analysis for this load combination, we go back to our von Mises stresses, and maybe I isolate this based on our base plate here for my visibility. And sure enough, I look at my highest stress here and it's 35.997. So nothing is exceeding that 36 KSI. Essentially, with this nonlinear material analysis, the program is going to apply the load. When that FE element reaches the yield strength, then the load is going to be distributed to the adjacent elements. It continues to do so until the load is fully distributed. And we can actually see within our static analysis as well, the option for the criteria. So we activate the criteria and the program will tell us exactly which elements have fully yielded. Perhaps we go back to our von Mises stresses and maybe I show the reverse visibility here. So we're only viewing our columns. And again, the highest stress is 49.819. I should never see any of those element stresses higher than that 50 KSI. So that's as far as the static analysis, but under the stress strain analysis for the actual design, we can view here the stresses on the surface, and I'll cancel out on my visibility so everything's visible in my table. And I would also expect not to see any stress design ratio higher than 1.0. So within the existing stresses is this column here. The limiting stresses either 36 or 50 KSI, and here are the stress design ratios, 1.0, 0.996, 0.989. Again, because we're never exceeding that limiting strength. So within these table settings, we also can view the strains on surfaces. Remember, we activated that, so we see the existing strains, but we also have that limit that we have input in that's only applicable for the nonlinear material analysis. And then we get a strain plastic design ratio here as well. And lastly, remember the stress ranges on surfaces. I said that we could activate this. We will show the minimum stress with each surface, the maximum stress, and then the total range here. And everything's synced up in the background here. We can see that red arrow showing us exactly where those high stress points are. And of course, we can view everything graphically here, such as our stress ranges. We can view the stress design ratios. And remember, that's because we use this drop down here for the stress strain analysis. Now, that really encompasses here the nonlinear material analysis. The final thing I want to cover with this particular model is a new feature within RFEM 6. So I'll go ahead and turn off my results here. I'm also going to turn off my FE mesh, so this is a little bit more visible. And we want to take advantage under this option, folder option types for lines, we have the new feature line welded joints. And this is really a post-processing tool that we can actually do the weld design. Now, we're not modeling in the welds for the analysis, but rather we can take advantage of the program calculating the stress flow between surfaces, and we can set our weld joint here and give it the input data. We can also set the limiting stress value and to actually get a design ratio for these welds as well. So let us take a look at what this encompasses. So we activate this line welded joints and we have our first definition type here. The first joint type is a butt joint, but we also have a corner joint. And notice this picture updates over here on the right. We have a lap joint, and finally we have a T-joint, which is what we'll be utilizing today based on a double fillet. So what we will do is to specify the weld size. So perhaps I set this at 0.167 inches, and then I can graphically assign this weld to a line in my model. So we'll begin with the web that is going to be welded onto the base plate. Then I need to select my surfaces. So I first choose this vertical surface, and then my second click is going to be the surface that it's being welded to. So the order that you choose these surfaces does matter. So we'll go ahead and choose surface number 8, then 1, and we click OK. Well, I can make a copy of this line welded joint, and what I'd like to do here is to modify the weld size to maybe something slightly larger, 0.25 inches. And then I'm going to choose my line of my upper left flange. I then choose my vertical surface first, my horizontal surface second, but I can remain within this dialog box to add a new object. Now I can rotate this around here. I can choose my second line weld joint. I choose my vertical surface, my horizontal surface. I once again add a new object to choose the lower left flange this time, my vertical surface, and then my horizontal surface. And one more time, I create a new object by selecting my right flange with my vertical surface and my horizontal surface, and I click OK. So now we see all of those lines and surfaces generated here with the relevant line welded joint definition types. So now that we have defined these line welded joints, you'll also notice within my stress strain analysis that we have a new option here called line welded joint configurations. So if we take a look at the default settings here, once again, we have the various stresses that we can calculate based on this new weld. So we have here the weld throat stress due to normal loads, due to bending loads, shear loads, and so on. Well, for this example, I'm going to activate all of these stresses here along my weld based on those various loads. And then I'm also going to activate the resulting weld throat stress, which is really combining all of these stresses into one to come up with that equivalent stress. Under these special options, this is telling the program how do we want to smooth those stresses along the weld in order to calculate the stress design. So we can just set this to none for right now. And all this means is that the program won't smooth those results, but perhaps we're doing a hand calculation. Maybe we'd want to change this to linear or to constant for a little bit easier comparison as opposed to comparing to the none option here, which won't smooth over those results at all. The stress distribution for the fillet welds can be set to simplified here. We also can take advantage of the weld eccentricity within the calculation as well. So now that we have set all of these various settings, we also have the ability here to set the limit stress type. So currently it's set to none, but we can use the option here user defined, and for this equivalent stress, we would input in the strength of our weld. So perhaps this one's 57 KSI, for example, or whatever it may be. So now that we're done with these configurations, we click OK, and under the stress strain analysis input data, notice that we have here a new option to calculate the line welded joints, which is automatically turned on. So we can run this calculation here directly within the table. The program needs to run through this load combination, and we're still running that nonlinear material analysis, so keep that in mind as well. And then it will run through the stress design. So we've already covered the stress design of the surfaces, so rather what we'd like to do is to take a look at the stresses in the line welds. And I'll turn this to wireframe view. We can kind of zoom in here to see exactly what's happening. But we see for each one of these lines that we applied the welds, we have the existing stresses. We have our limiting stress here for that equivalent resulting weld throat stress. And then we get a stress design ratio as well. So we also have the options to view these graphically here, and you can see the line weld stresses. We can change the view of these. So that option to smooth over the results, this is what I was referring to. Essentially, the program can set this to a linear distribution here, constant, again, if we're maybe comparing to hand calculations. Otherwise, we won't have any smoothing going on. And of course, the stress ratios are shown here as well. So kind of a great new feature, again, that we added within RFEM 6 that will be helpful for some of these FEA connections. All right, so we will move on to our final example today, and this one should go rather quick. This is a 3D solid. So notice that I went ahead and modeled everything here, and we have all of these available surfaces in the model. Well, when we're modeling solids, we set the boundary surfaces to define the solid here by choosing the stiffness type without thickness. So there's no thickness, no material. We're simply using them because when we generate our solid, notice we have here the boundary surfaces. And with the solid element, we do need to give it a material. And in this case, I gave it the material of A36. So I also have a couple load combinations already generated. We have an upward load here right through the openings of this solid. We also have a downward load. So these two load combinations are going to be categorized under my design situation. And we want to right click here to visit our base data. And this is where we can turn on that stress strain analysis. We click OK, and now we get that additional folder over here on the left. And similar to what we saw previously, we now have a solid configuration. So we double click on this, and of course this list looks a little bit different because now we're working with a 3D element, so essentially FE elements in all three directions. So we have some suggestions here, such as the maximum shear stress, the maximum axial stress, but we'll go ahead and just check the von Mises stresses once again. We see the relevant equation given to us here. The program should refer to that 36 KSI for the limit equivalent stress. So once we have set the configuration settings here, we can click OK. And under the stress strain analysis, we can take a look at the design situation as listed here, but under the objects to analyze, we don't want to design these surfaces. We'll actually just end up getting an error anyway that we can't design them because there's no thickness or material assigned to it, but we will design this solid. We also can activate that stress range if we'd like. And realistically, we can run our calculation. So we go to calculate, calculate all. So very similar workflow here for our 3D solid. We're going to essentially calculate the load combinations here. And then once the program is done doing this, it will move on to the stress design within that add-on. Now notice this does take a little bit longer because we've introduced FE elements now through the thickness of this object as well. But once we're done with the calculation, we're currently viewing the static analysis here. We can take a look at our stresses, for example, such as the von Mises stresses. And we see the von Mises stresses for that downward load as well as the upward load. But jumping to the stress strain design, well, we can view the stresses on the solid. We see here the existing stress from the von Mises, our limit stress of 36 KSI, and that stress design ratio here of 0.865. We also can view those stress ranges on the solid as well. So the minimum stress, the maximum stress, and the stress range. Just a couple of quick features that I wanted to point out with the solid element that are either new or improved within RFEM 6 as well. If we go back to our navigator under the data, We have under the guide objects what's called clipping planes and clipping boxes. So if we create a new clipping plane by double clicking here, we can create multiple clipping planes at angles. We can define them by 3 points, or we can simply offset from the XYZ axes. So perhaps I set this parallel here to the YZ axes, and I can set my origin graphically by clicking within the model. I click OK and set. And let me go back here to the static analysis and we'll view our von Mises stresses. But notice you now can view those von Mises stresses throughout the depth of the element, or kind of in the interior of this solid. We also can go back to that clipping plane. We can double click to edit it to invert it. So if we're interested rather in seeing the other side of those von Mises stresses. So you can see that we can create multiple clipping planes, and we can simply turn them on or off by right clicking here and deactivating it. And now we're back to the full view. Same concept for the clipping boxes. So we can create a new clipping box here and we set the origin. And this time with the clipping box, we need to give it 3 dimensions. So we'll give it maybe 1 inch in the X direction, 1 inch in the Y, and 6 inches in the Z. I click OK and set active. And now we have this clipping box throughout the depth of that solid to view the stresses in the interior within these defined settings. So again, we can see the clipping boxes here can create multiple definitions and can turn them on or off by just right clicking. So that's a little bit more efficient now that we're in RFEM 6 for viewing various results with those solid elements. Okay, so the final thing to touch on quickly, as I know we're running out of time, is just a very quick printout report. And we can create a new printout report up here in my toolbar, or we could create it down here in our navigator. We create a new printout report definition here. And notice the program gives us all of the various input as well as results that we can turn on and off. We also can load some saved templates here. So we have default templates, including the stress strain analysis, where we've kind of turned on some of the information we think you'd be interested in. You can create your own template for the printout report. For today's quick example, I'll go ahead and uncheck everything here, and I can right click to collapse all these folders. And we're only going to activate the basic objects. I'll activate my solid input data, for example, and then under the stress analysis, I'll input some of this input data as well as my results. We'll view here the stresses on solid as well as the stress ranges on solid. And I can simply click Save and Show. What the program will do is to open up a separate application here for my printout report. So pretty small printout report for today, but you can see here our header. We can modify this logo to maybe our company's logo instead. We can modify a lot of this input data. We see here a nice picture of our solid, and of course our input data in table format as well as our results. So pretty quick printout report for today. But what we can do is to actually drag this printout report maybe to a second monitor and work concurrently within the RFEM program. So any modifications will actually update in the printout report in real time. And perhaps we'd like to add just one graphic to this printout report quickly. And currently I'm viewing my results here for this upward load. And remember, we have this set at our von Mises. So I'm going to add this particular picture to the printout report. Well, we have a nice feature here under the display, and it's called ISO bands. And this is new within RFEM 6 that we can activate what's called the gray zone. The gray zone just allows me to set certain percentages here of maybe stresses that I'm really not so interested in. So notice those low stresses are now grayed out. And we can continue to increase this until we see, all right, we're pretty content with viewing only the stresses that are of interest here, and everything else is kind of grayed out, those lower stresses that are not so much interest. So we're ready to add this particular graphic to our printout report. So we can go up here to print the graphic to the printout report. And what else is nice is that we can make some changes here. Notice this is set to window filling, so the picture is zoomed in now to take up the entire page width. But I'm also going to activate here the 3D picture in the PDF. So this is currently off by default, but we'll go ahead and activate this. If I click Save and Show, I'll drag my printout report back here, and what we'll see is this picture added to the printout report. Now, nothing seems so special about it now, but if we take this report and we export it to a PDF, and we choose some location here on our computer, we save it, the program will automatically launch whatever PDF application we're using. And in my case today, I'm using the Adobe program here, and we see the same printout report. But I scroll down here to that picture that I just generated, and what you'll actually find is that this is a 3D picture. So this is really nice in the sense that within this PDF now we have the ability to kind of rotate and to view those different stresses however we see fit. Will be nice to send to clients, especially for some of these objects that maybe we don't want to create multiple printouts of different orientations of the stresses, but rather we can just send them this 3D picture directly. So just wanted to mention that's kind of a nice feature within the program. All right, so we will go ahead and conclude our webinar today. You can always visit our website at delubal.com to learn more about RFEM, to learn more about these add-ons that you saw today, including the stress strain analysis. You'll be able to download these models on the same page that you registered for the webinar. Those will be posted within the next day. You can open them up within the free 90-day trial version of RFEM, and after the 90 days, it will turn into a demo version. So if you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office. You can see that contact information shown here, our phone number, as well as our email, info-us@delubal.com. So we will have many more upcoming webinars. You can register at delubal.com under support and learning webinars. As most of you know, I will send out a reminder email about a week or so before these take place, so feel free to register through email as well. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the states that we are pre-approved provider, that you are here for the full 60-minute duration in order to receive that PDH. Now, this isn't automatic. The PDH will usually be sent out within the next day. So again, it's not going to be sent out immediately after the webinar. So just keep an eye out for that within the next day or so. If you watched it with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar with your own name and your own email, please go ahead and request that PDH at the email address you see here, the info-us@delubal.com. Again, if you did not register yourself, you were here for the full presentation, just go ahead and send us a message of who you watched it with, and we can go ahead and generate that PDH for you. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at the next presentation. Thank you.